So I'm very happy to be here, and I'm allowed to talk a little bit about the universe. Unfortunately, the universe is dark, and we have to have these spots for the film. And I'm supposed to stand here, which is very hard. I tell you, this is the biggest challenge, not to walk around, because once you get excited, it's impossible to stand still. And I do my very best. My son is here; he keeps control over me. And I would like to talk about the Big Bang and the emergence of life. And it's a very timely topic because we just got 42 million euros to understand how life forms in the universe and whether we are alone. We have 7 years to do it, and we'll see how far we get. If we don't completely figure it out, we might get another 7 years, 42 million. So we'll leave a little bit behind for the next 7 years. And I would like to start this talk with something you should all know, which is our Earth. And as you know, we live on this Earth, and we take our life so serious, the Earth so serious, that we never think about that the Earth is actually something quite different. It's something very, very small. And in order to see this, you need to walk away from the Earth, like the Voyager 1, which is a little spacecraft that is now at 6 billion kilometer distance and a little more, and made a picture of the Earth. And you see it here. This is our Earth, the famous pale blue dot. And when you see the Earth from this distance, you begin to wonder. You know, we all live on this little blue spaceship. And we have, as we just heard very nicely, not a plan B, not another place to go. And we mess it up, and we pollute it, we destroy it, and we do not even care so much about it. And I think everyone, there are some presidents, I don't want to mention, who should have a view, look at this, and they might then get a different impression. Just to tell you, there's something I'm doing right now with the International Astronomical Union. We want to show the pale blue dot to every child on this Earth, because we think the children will be the future. And if they see the Earth from this distance, how vulnerable and how beautiful it is, they might not do it as we do it, but a little better. So that's our hope. Now, there's something very fascinating right now going on. And this is that we are in understanding our universe. It's the golden age of astronomy. And it's something which is rather special, and you should really enjoy it. Because it's like Richard Feynman said, we are lucky to live in an age in which we are still making discoveries. It's like discovering America. You only discover it once. And you might sit here and you might say, okay, I don't know whether there's life out there. Maybe in 10 years we know there's life out there. And you will tell your children and grandchildren, look, they will take it for granted. But you will tell them, look, I thought I might be alone. They will not believe you. And it's amazing. So enjoy every second and see how astronomy and science makes progress. And I would like to start now with the beginning of this world, the beginning of the universe, which we know very well. The origin of the universe was the Big Bang, 13.6 billion years ago. Before the Big Bang, there was nothing. Absolutely, not space, nothing. And then suddenly, out of nothing, our universe formed in the so-called Big Bang. And initially, the universe was tiny, very small and extremely hot. And people usually think the Big Bang is everything, and then it's just simply evolution. No, actually the universe is right now being created. The Big Bang was only the beginning, and if there would only have been the Big Bang and the universe would have stayed small and hot, nothing would have happened. There were no fluctuations, there were no structure, there was not a chair on which you could sit, there was not the oxygen for water. Water didn't exist. The idea of water didn't exist because oxygen didn't exist. In the Big Bang, there was only hydrogen and helium. This was all, and with that, you can't really build life. And if that would have been all, nothing would have happened. And if the Big Bang would have been all and the universe would have been small and hot, it's maximum entropy. You can't get any structure. But the universe then created something. The creation right now happens. You know what it created? Space. It began to expand. And it's still creating space. And because it creates space, it cools. And then suddenly gravity becomes important and begins to form structure. And we can simulate it here. You see it, the large-scale so-called cosmic web gigantic filaments of sizes millions of light years. A light year is the distance which light takes in a year. From here to the moon, it's just a light second. So these are gigantic structures of gravity which become possible because the universe creates space and cools. And then in these centers, that is where the galaxies form. And the galaxies are the building blocks, the islands of the universe. And within the galaxy, we are currently sitting. And I will tell you about this, our Milky Way galaxy. Now, additional structured forms, and one of the most beautiful structures is our solar system. And here you see a picture, a sketch of our solar system, which consists of 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. But there's much, much more in this kind of solar system. And we like to understand how it forms and what it means. Is it a peculiar place or is it typical? Now, if you would be an extraterrestrial being, you would visit the solar system. Naively, we think they would be interested in the Earth. But that's not right. You know, they would look at the biggest structure in the solar system, and that is not the Earth. The biggest structure is the gigantic Jupiter. So they would probably look at Jupiter, they would probably miss Earth completely, and then they don't find life on Jupiter and then disappear again. So, you know, Jupiter is the giant of our solar system and the most important object, so to say. Yeah? You already begin to realize that we are not really that important. And I will tell you, the farther I go, the less important we become. And this is really, really good. I tell you, I will never get a heart attack because I have been humiliated by the universe. I don't find myself important anymore. I just enjoy it. And that is good for anyone. So you will see later on. And the interesting thing is actually Jupiter, which you see over here, is made out of the basic building blocks of the universe, hydrogen and helium. It still contains most of that old stuff. And Jupiter is really big. You see here Jupiter, here you see the Earth, and this is a storm on Jupiter. The Earth is smaller than a storm on Jupiter. And you might now wonder, what is that in there? What is the Earth made of? And you know very well there is hydrogen, you drink water, but it's not dominant. You are not made out of hydrogen. But this didn't exist in the universe when it formed, so it must have been created later on. And you know what you are? You are stardust. You formed in a star, and then the star ejected the particles, and that you're made of. You are really, really stardust. And these 4 inner planets are made of this very peculiar stuff which wasn't there when the universe formed, which formed later on. Actually, there's more stardust here. This is the asteroid belt. This is a region of lots of asteroids which never formed a planet, could have formed a planet, but didn't for some reasons. And actually, you see stardust once in a while. When you look out in the sky, you might see a shooting star. What happens is, because our solar system is full of all these little particles of stardust, the Earth collects it. About 1,000 tons per day of stardust fall on the Earth. And that is beautiful because this little dust particle lights up again like a star when it evaporates in the atmosphere. And that is a wonderful idea. It was light in the star, and it's light again when it disappears and falls onto the Earth. Well, sometimes stardust can be a little bigger, like here, some 10-kilometer sized asteroid, and then it can basically destroy civilization. After such an event, you know, it will be different on this Earth. And we know it will happen 100% in a million years or so. It could also be tomorrow. It's like, but it's like San Francisco, beautiful city. I go there every year, but you know, the earthquake will happen, the big one, and who knows when. And I think we should do something to prevent, you know, the dinosaurs were too dumb, they couldn't do it, but we can do something. It just, we have to sit down and get it done. Protecting the Earth against this kind of events. We know how to do it. It has never been tested. It should be done. And we have a little Fragile World Foundation with Philip Schöller, who is sitting here, where we try to get something done. And okay. Anyway, let me now move to the center. In the center of the solar system, there sits a star, our personal star. And this star, you know very well, is the sun. And the sun is really, really amazing. You need to appreciate it. The sun is bigger than Jupiter. Here you see the sun, part of the sun. This is Jupiter, and the Earth is, this little spot over there. And it's good that the sun is so big, because it burns and shines. Actually, the temperature on the surface of the sun is 6,400 Kelvin, 6,400 degrees. It's precisely the temperature we need for liquid water to exist on Earth. If the sun would be a little hotter, it would evaporate. If the sun would be cooler, it would be ice. And look, the fascinating story is the sun shines with this 6,400 Kelvin for 4.5 billion years. It's absolutely stable. You know, if you have a chimney and you put in some wood or so, and you don't take it seriously, suddenly the chimney goes out, and you freeze. If the sun would want to go out for a day only, we would die. The sun has been doing this for 4.5 billion years. It's really important. You know why? Because life is the oldest object on Earth. If you look at stone is 100 million years old or whatever. Can't be older because it's basically melting when it moves into the interior. Life exists for more than 4 billion years without turning off, because then it would have to restart. And you need something which is absolutely stable. And this beautiful star has been stable for 4.5 billion years. Now you might wonder how the star does it. Where does the energy come from? And you can't see it. E is equal mc square. This is Einstein's formula. Energy is mass times speed of light square. And what the sun does, it takes its own mass and converts it into energy. And with this, it shines, and of course, becomes less massive. Now, how does it do it? Well, it turns hydrogen into helium in the so-called fusion process, taking 4 hydrogen atoms, making 1 helium. And the fascinating story is, if you weigh the helium, which is 4 hydrogens, it's lighter than the 4 hydrogens. So a little bit of mass is turned into energy, beautifully. And with that, the sun can shine. And actually, the sun loses every second 4 million tons. I sometimes wonder, after a good dinner, it would be nice if I could turn mass into energy too, but it hasn't yet been able to figure that out. So why can't we figure it out? We tried to invent the fusion reactor, but we can't do it in all details. The reason is, in order to have the fusion, you need 15 million degrees. And if you have a plasma with 50 million degrees in a reactor, you can't control it. It burns through everything. It's very, very hard. Well, the sun does it because it had this enormous atmosphere around it. You know, this layer of millions of Earth masses. So maybe we have to invent a sun. We have to put our fusion reactor into a sun with 1 million Earth masses, then it works, which is a little hard on Earth. Well, another aspect about the sun, because it's so fascinating, we are not living next to a sun, we're actually living in the sun. Because the sun has a wind. And the wind extends far beyond the solar system and protects us against all the things that come from the outside, from the interstellar medium, which could damage us. So we actually, the sun is like a, how do you call it, a henne, with the wings, yeah? And we are in the wings, and we look out and sometimes try to watch the universe. Well, but there's a problem. The sun turns hydrogen into helium. We have now half time, 4.5 billion years, but there will be a time where in the center, which has 15 million degrees, the hydrogen is used up. Must be so at some point. We know precisely when it happens, another 4.5 billion years, then the sun has used up the fuel. And then it will begin to expand, and it will become what we call a red giant. It will become so large that it swallows the inner planets and evaporates everything on the surface of the outer planets. Life will disappear on this Earth. There's no way we can get rid of it. It will happen 100%. And I tell you, so we still have a little bit time to go, but it's 4.5 billion years. But I have to tell you, these dying stars are one of the most beautiful objects in the sky. The sun expands, it then ejects the outer envelope What is left behind is the burned out core, which is called the white dwarf. And here you see one example, Cat's Eye Nebula. This is one of a sun which is right now exploding. You see the white dwarf in the center and the other parts are thrown away. And if you look around, this is the Eskimo Nebula. Every exploding or dying sun is different. It's a unique picture in the sky. And I'm really looking forward to see how our sun will look like in 4.5 billion years. Well, okay, you might say, fortunately, there are other stars. So let's pack and move. But I tell you, it's not that easy. There are many stars. In the sky, the world of stars, if you look out in the dark sky, you see all of these spots in the heaven, and that are stars like our sun. And actually, if you look at carefully, you see that all these stars are in a line. Now, if you look in the visible regime of the light, where our eyes are actually sensitive to, you see there are lots of dark areas. These dark areas is not the Milky Way broken up, but there is a whale of gas, gigantic gas clouds, which are sitting between us and most of the stars. And they block the light of these stars, and that's why it looks like darkish. You can really see it. And if you look in the infrared, you can take away all this kind of stuff in the infrared. This gas is optically thin, we say, and then you see this beautiful disk of the Milky Way. It's really disk. And we see it edge on because we're sitting in the disk, and that's why this disk appears like a line on the sky. But it's a two-dimensional structure. And actually we know this because we see other disks. This is another galaxy. The same story. Here you see the gas again, and once in a while you see disks from face on, and then you see really it's a round object. And so that's how our Milky Way looks like, a disk of stars. And now you would like to know how many stars are there. And that's why we have our students, because they count. And when they have counted it, they get a big number. There are 100 billion suns in the Milky Way, each surrounded by a solar system. Then you can think there must be lots of life out there. Now you would think we are, of course, sitting in the center of the Milky Way. Wow, that's completely nonsense. We sit somewhere lost at the outskirts. A little star, one of 100 billion stars in the outskirts of the Milky Way. And the Milky Way is really, really big. Look, our sun moves around the Milky Way center, which sits here. Like all the other 100 billion stars, all moving around in this rotating disk. And it has an enormous speed of 800,000 kilometers per hour. That's big. And if you just want to experience it, go to bed at 10 o'clock, wake up the next day at 8 o'clock, 10 hours later, you have moved on 8 million kilometers. No wonder that sometimes you feel a little distracted because you are somewhere else in the universe. 8 million kilometers from where you got to bed. But still, with this enormous velocity, you still need 200 million years to orbit once around the center of the Milky Way, which really tells you the Milky Way is a big object. In fact, this is good so, because, look, we have a problem. We say hello to the outskirts, to whoever is out there, because we generate radio emission. And all of these radio signals leave Earth, and we can't get them back. And guess what kind of embarrassing things are in these signals? Somebody saying something, all the wars, everything travels out into the universe, and everybody can hear us. And don't think that they are always happy with us out there. They might say, well, this is a dangerous population. We better get rid of them. They mess it up already. So it would be better if we would be more careful in shielding ourselves instead of saying, look, here we are, and we do all these kind of bad things. The good thing is because the universe is so big and the Milky Way is so big, the 100 years of radio signal is 100 light years, hasn't traveled very far. It's this kind of circle here, which is in this thing, so really not that far. So that's good. But it's eventually, we'll hear from other civilizations. Now, I wanted to tell you what happens when the sun explodes. Can we go somewhere else? And in fact, we can look around. And you don't have to look very far. You take the next star. It's called the Alpha Centauri system. Consists of two big stars and a small star, Proxima Centauri. Proxima Centauri is a red star. The next star, it's a red dwarf. It's smaller than the Sun, and you might say, okay, I don't want to deal with a small star, I want big stars. But I tell you, small stars are better, because they live much longer. Red dwarfs live 1,000 times longer than the Sun, because they have such a low temperature that they don't waste all of the energy. And none of these red dwarfs have ever exploded. The universe isn't that old. We don't even know what they become of. So better go to this little thing and live a long life than these big things which live very shortly and you have to look around again. I mean, that doesn't make much sense. So Proxima Centauri is something to go to. Okay, and indeed, a planet has been found around Proxima Centauri right in the habitable zone. It's closer to this star so that there would be liquid water. Perfect. Now there's a problem. When you want to go there, you can easily miss it. But this is Alpha Centauri. You don't have to go there. Yeah? Don't mess it up. You have to go to this little red spot over there. And there's no GPS as far as I know out there. So you might miss it. Yeah, we call out these stars. And there's another problem. It's quite distant, even with this being the next star. It's distant. Just to demonstrate that, Voyager 1 already mentioned, the pale blue dot. It's moving with the fastest velocity ever a spaceship has ever gotten, 62,000 kilometers an hour. Now, suppose this is our velocity. And you might say, well, okay, maybe longer, but faster, but you know, we have to take lots of bottles of beer with us and all of this. My wife has usually 5 suitcases. You know what it is. It accumulates. And so maybe this is the maximum velocity we can have. Then we want to go to Proxima Centauri. Guess how long it takes. You know, Proxima Centauri is 4.2 light years away. The light needs 4.2 years to go there. So what do you think? How long does it take? 74,000 years. Now think about it. This is 2,000 generations. So you leave, you die, next generation dies, next generation. After 3 generations, they get so fed up with each other, they kill each other. After 5 generations, they have forgotten why they started. At home, the people have already replaced the launch pad by an amusement park because they completely forgot about us. Yeah, and then you continue, and after 2,000 generations, you arrive at Proxima Centauri, and then it's already occupied. You have to continue. Where do you go? I mean, we are not made for space travel. And I think that might change. You know, we now begin to change our genome. And I know it's dangerous. But if something is dangerous, it doesn't tell you shouldn't do it. We need to accept always new technology. You just have to keep it under control and make the best out of it for mankind. Yeah. So, but this might be a way to become older, to really live for 1 million years. And I think that is the reason why we haven't been visited by extraterrestrial life. People say, okay, if there would be extraterrestrial life, they would have visited us. Sure, but not in this 100 years we can think. Yeah? Look, they can only travel the universe if they live for millions of years. And that means before they visit Earth, they might go over there to another place in the Milky Way just to get a coffee, and then arrive 100,000 years later. Yeah? 100,000 years from now, we're already dead. 100,000 years in the past, we wouldn't have noticed it. For them, it's nothing. For us, it's all. Just arriving right now in the last 1,000 years is unlikely. So I think that is the argument. And we might do it if we live longer, but who knows? Well, you might wonder where all these stars come from. Were they always there, or were they created or something? And indeed, you see it in the sky. But you need to look at it with infrared eyes. This is what you see in the sky in the visible. You see the beautiful Orion constellation. Everybody should look at this. It's especially well visible in the winter time right now. You see the belt of the Orion, here the shoulders, here the legs, and you can't miss it. I sometimes wonder, people always look at the Big Dipper, the große Wagen. I sometimes can't find it myself. But the Orion I always see. So it's much easier to find. Just look at the Orion when you go home. Well, I don't know when the sun will come out again. It's probably a few weeks from now. But anyway, so you know. But suppose you would have infrared eyes. You would not see the Orion. What you would see is this. You see something different. You don't even see the stars anymore. You see the gas in between the stars, the interstellar medium. And out of this gas, the stars are forming. This is the material out of which all of these stars are forming. And you see it here again. I showed you the Milky Way before. And you know, see this kind of darkish veil in front of most of the stars, between us and most of the stars. This is the interstellar gas which in the visible light absorbs the radiation. And in the infrared, it is bright. Yeah. And actually, here's an example. This is a big shadow which you see in front of many stars. You know, there are only a few stars between us and this shadow. And if you now look at the shadow in the infrared, you begin to see a gigantic gas cloud. A cloud of hydrogen and helium gas. Now, you might wonder, if you know a little bit of physics, how helium and hydrogen can generate light in the infrared. That's not possible. And it's not the helium and hydrogen that is basically what you see. It's a little particle. It's a little dust particle, just a micrometer big. But of this stardust, there's tons and tons, billions and billions of these little particles. They have a kind of radiation, which is Wärmestrahlung. What is this? You know what I mean? And with that, they radiate. Yeah, and that's what you see. And this stardust contains all the elements which we need for life. It's already there, just in little particles. All you need to do is now bring it together into a planet, store it in a planet, and then let life form on this little stardust. Now the question is, how does it happen? And we see it in this kind of cloud itself. Look, this here is a young cluster of stars, a young cradle of stars. So the stars are babies, just 1 million years old, not much older. And they form in the same cloud where all this beautiful stardust is sitting. Here you see another region of young stars forming right now in the cloud. They have burned a hole into the cloud, and you can actually watch star formation directly. And so we know that every year, somewhere in the galaxy, a star disappears, and probably a solar system disappears. But every year, and that's so beautiful, somewhere else in the galaxy, a new star is being born, which is amazing. And these pictures, these are not, this is not paintings. This is real pictures of the universe. They are so beautiful that if you show these to your students, they know why you become astronomer, and they want to become an astronomer too. And when I met my wife as a student, I hadn't much to offer. So I said, okay, I study where we come from and where we go, and I look at these beautiful pictures. And now we are married for more than 30 years. You see, it worked for me. And my wife is now painting these pictures. They hang in my office. They look a little different. I have to, she's not here, I have to admit. But she says this is the freedom of the artist. And she's right. They look even more beautiful, sure, of course. Now, what happens when you let such a gas cloud loose? And we have done numerical simulations to study this. This kind of reddish area is now the infrared gleaming part of the gas, and yellow is very dense gas, and when you see a white spot, this is a star forming. And you see the gas collapses, condenses into stars, and in this evolving cloud, you see a whole cluster of young stars forming. It's just what you see in the universe. You can simulate on the computer, and on computer, we have here the CEO of the LRZ sitting in the second row, and with his computer we can do it much faster than 4 billion years. Still takes a little bit of time, but he's always been very generous with us because he wants to understand it himself. I completely understand that. So, of course, that's not what you would see because you don't have infrared eyes. So if you would look with the visible impression on it, you wouldn't see much till you see the stars shining. The first star shining, second star shining, and then the stars begin to ionize the surrounding, heat up the surrounding, and then you begin to see the gas cloud around it, actually becoming brighter and brighter and brighter till the stars destroy the environment in which they are forming. And when a big star forms, then you see a big bubble of heated gas and so on and so on. So we can all study this here at Munich with the help of the Leibniz Rechenzentrum. And then we did something else. We looked around the stars and we found something amazing. You see this here. In the middle you see the bright spot, the star, and you see a red shadow around it. This red shadow is a disk, a flattened, fast rotating structure which is just the size of a solar system. The gas doesn't fall directly on the star. It has some angular momentum, we said. When it falls inwards, it spins up and begins to settle in a disk around the star. And we see around every star in our simulation, a young solar system is forming. Naturally, we don't have to put it in. It just happens by itself. So the formation of planets is a natural byproduct of star formation. You don't have to fiddle around. You don't have to put it in or whatever. It just happens because of this fact that the gas has a little bit of angular momentum. So the question is, we see these disks forming around the young stars. Are there disks around young stars? Do we see them? Can we even find the planets, and can we see life on the planet? So do we have evidence for disks? So here I want to show you again the Orion. It's over here. And now we don't focus on the stars, we focus on this little spot here. This is Orion Nebula, a star-forming region. And you see this here, the veil of gas, and the bright part is because the stars have heated the surrounding up. And then this was hanging at the Max Planck Institute for Astronomy in Heidelberg, where I created a theory group some time ago. And it was in a beautiful corridor, and we had school classes going through. These little kids, they are really, I tell you, they are it takes most energy. Not to keep them from not listening. They listen and then they ask the most nasty question. They don't even behave. You know, they ask something I can't answer. It's amazing. I don't know how they do it. And there was this little girl, and she was looking at this picture, completely amazed about this gigantic cloud and the stars forming, and said, okay, well, there's dirt in this picture. And I said, what, where's the dirt? And she began to look at this, showed me here, and said, was beginning to scratch. And I said, don't scratch my nice picture. And what she did, and then actually I saw, do you see there's a dirt here? I blow it up a little more. It wasn't dirt. It's a young solar system forming around a young star. And this little girl accidentally had discovered it. Amazing. I don't know what she is now. Probably earns much more money than I ever will earn or so, but anyway, so this is you always discover something else. And so we know that indeed around each star there are disks forming, like what we get in this numerical simulation. And these disks are full of all the stardust which we brought in, all of these pieces out of which you can form planets, asteroids, and life. Now, there's a problem. You know, we are not in pieces of millimeter-sized objects. We are big, and the Earth is big. So you need to bring the stardust together. And this is actually easy, and it's an experiment that runs under the bed, under our bed. Have you ever looked under your bed? If you don't vacuum all the time, there's a little bit of stardust. And we keep this stardust under the bed for scientific reasons. We don't clean it. Yeah? And I tell you, this is amazing. When you look at this Staubwugel, we say in Bavaria, actually I have to stand here, you know, this ball of dust, and look at it a month later, it becomes bigger. And if you would wait 1,000,000 years, it has formed a little planet. And that is what happens in these kind of disks. All the time, the stardust just accumulates and forms the planets in these disks. Now you might wonder, where is this kind of stardust coming from? Of course it must come from a star, but we told you hydrogen goes into helium in the sun, and then the sun explodes. And that is not really stardust. But we have bigger stars. We have gigantic stars. This is an example. This is Antares, and you see how big it is? This little dot here is our sun. It's a gigantic star. And these stars are the alchemists of the universe, because they do not only turn hydrogen into helium, they use the helium and turn it into carbon, nitrogen, oxygen, all these beautiful elements out of which we are made, and out of which the plants are made. And the other thing is they live short, because we want all these elements out in the universe so that we can form planets. So they live very short, only a few million years, and then they explode as a supernova. And for about 2 weeks, they shine brighter than all the 100 million stars of the Milky Way together, and then they die. But in this explosion, they throw out all this beautiful stardust into the interstellar medium, this gas, and in this gas, new stars, and now also planets can form. And it's really fine-tuned. We have these little stars like the sun that they burn forever, but they can't produce much elements. And then we have these big stars who generate all these beautiful elements and evolve very quickly. It's really a fine-tuned universe we are living in, just made for life to form. Now, you might say, okay, we know professors talk always, and can you really actually demonstrate we are stars? Well, I can, because this is the abundance of elements in the universe. Here's how frequent an element is. You know, the higher the point, the more frequent. Here's the atomic number, hydrogen, helium, is what formed in the Big Bang. And then you see the next group of elements, which are the most frequent ones, are oxygen, carbon, and nitrogen. This is this group, and we find this always in the stars in these exploding supernovae. So this is what the stars produce. It's the rest of the stars. And here you see the chemistry of mankind. HOCN. HOCN. And a little bit of phosphor and whatever. So the nature has just taken what is around, the debris of the stars, and has made us and the Earth out of that. And it's so amazing. You know, you're really important if you think about it. You're not the most important in the whole universe, but you play a role. And I think I like it. And I would just want to show this animation of the Milky Way, where all of this happens. We go out, we move out into the Orion. Here you see, if you can see this, these are the veils of gas and dust, and the bright part are the stars. Here you see a star-forming region, the Horsehead Nebula. In the back you see is an exploding supernova. This is over there, the Crab Nebula. This is the gas cloud which has burned a hole. The stars have burned a hole. Now we turn around and we look into the center of the Milky Way. And it's good that we don't sit in the center, because in the center is a gigantic black hole. It's a beautiful object because it's a gateway to another world, but I don't have time to talk about this. You need to invite me again. And then we move out of the Milky Way into the intergalactic medium. There's more around the Milky Way. You know, you see the Milky Way from the outside. And what you see now, these are not stars. These are Milky Ways like ours. We pass the Large Magellanic Cloud, the satellite galaxy. This is the Andromeda galaxy. It's twice as big as our Milky Way. And then you see in the distance here this kind of stream and filament of galaxies. Thousands of galaxies in the universe. And there's a galaxy cluster. Gigantic galaxies, hundreds and hundreds and thousands of them. And actually you can count how many galaxies exist in the visible part of the universe. And guess what? 100 billion galaxies, each with 100 billion stars. So even if life could form only once in a galaxy, it would just simply bloom of life everywhere. That's why I think life is everywhere. Because why all of this things, it would be waste if just life could have formed here on Earth, and that was it. And then we mess it up, we destroy ourselves, and all of these billions of galaxies for nothing. Doesn't make sense. For me, life is everywhere because it's a natural product of all of that. So the question is, can we actually find life? And we have been looking, and we are getting farther and farther, and we actually detect distant worlds. Now the question is, how do you detect it? There's a problem. You know, when you look at the solar system, I told you, you would see Jupiter. But Jupiter is already 1,000 times smaller than the Sun. And so you really have to be very close. If you're far away, even Jupiter wouldn't shine. Only the Sun is what you would see, because the planet doesn't shine by itself. You can't easily see it. So how can we discover planets? Well, I told you these planets form in these disks. And when the planet forms, and you can see this here in this animation, in the simulation which we did, it accretes material from the surrounding. This is in the co-rotating frame, basically from looking from the outside. This is in the non-co-rotating frame from the outside. This is in the co-rotating frame. We rotate with disk, and so it stands still. But what you can see is the planet accretes material, not from everywhere. It accretes material in a ring-like or spiral-like structure. And even if you can't see the planet itself, if you find the spiral of accretion, there's a good evidence that something is accreting it. So we have been looking for spirals of accretion. And that was something which was in 2011 an image of a star-forming disk. You see the disk is too blurred. We didn't have a resolution. But then came ALMA, a new telescope, one of the biggest. And with ALMA, we could for the first time resolve these disks. And guess what you see? Lots of rings and spirals of creation. Wherever you have these gaps, a planet is probably sitting and accreting material, a young planet. So you don't see the planet, but you see the footprints or fingerprints of this planet very clearly. And we see this now everywhere. Whenever we see young disks, we see something accreting and generating the rings. So that's the first evidence that planets indeed are forming there. But there's more. You can get closer to a planet by looking at a star. Here you see the star, here's the planet, which is not visible, but what happens is the planet is not only moving around the star is also moving around the planet, because gravity works the same in both directions. Not such that the Earth attracts us, we attract the Earth too, with the same force as the Earth attracts us. And so both planet and star wobble around the center of the same center of mass. Let me see whether I can do this again. No, here you see it. There's a center of mass, and both wobble around the center of mass. We cannot see the planet, but we can see the sun wobbling. How can we see this? Well, when the sun moves towards us, the light becomes a little bluer. It's like a Doppler effect. Yeah, it's like a police car or whatever, you know. And when the sun moves away from us, the light becomes a little redder. And we can measure the phase shift of the light easily. And there we know there's something wobbling. The sun is wobbling, and that means something is orbiting around the sun. We don't see it, so it must be something small. Either it's a black hole or it's a planet. There can't be much else. So with that, we can get already an idea that there must be a planet around it. But there's more. Now, if you have this kind of constellation again, but you're actually looking at the orbital plane of the planet from the side, then you see the planet crosses the surface of the sun. And when it crosses the surface of the sun, you get a dip in the light, because the planet's area is basically blocking the light. So we have been looking at dips of light, and through the dip and the amount of dip, we work out how big the planet is. Through the wobbling of the sun, we work out what the mass is. We know how big the planet is, we know what's its mass, we can work out its density. We can understand, is that a gas planet, is that a planet which has water, or whatever. We get already insight about this. Not only that, we can also do whole planetary systems, because each of these planets, when we look at it from the side, is actually affecting the light which we get. So here's the first dip of a big planet, you see it here coming up, and then this disappears, goes up again, then the second planet comes in, does another dip, and the third planet comes in at almost a little later. You get a second dip on the top of the first dip. And so we can work out whole planetary systems very easily and get the structure of the planets. We know, are these rocky planets or gas planets like Jupiter? It's very, very easy. But you can do a little more. When the planet is next to the sun, and you make a spectrum of the light, you take the light apart into its various wavelengths, then this contains information about the atmosphere of the sun and the planet, because every chemical element generates a special amount of light. And you can actually take this spectrum and take it apart. Now you don't know what is planet and what is sun. But when the planet is behind the sun, you only see the spectrum of the sun. You subtract the spectrum of the sun from the total spectrum, you get the spectrum of the planet. And you will see, is there pollution? Then that's probably life in the atmosphere. Or oxygen. Then ozone. It's a very clear non-equilibrium process indicating there's something special. It's not what you get in equilibrium. And through that, we are now getting first indications that there's something unusual around some of these planets. And I can tell you more because I'm embargoed on that. So, how many planets have we found? with this kind of transit method? Well, we had a little satellite, Kepler, launched 2009, running till 2013, 4 years, looking at the closest stars and looking for dips in the light. You have to do it from space because on Earth it's very difficult because the atmosphere of the Earth distorts the light. You have to do it from space. So Kepler looked at this, and that's what he got. This is the number of new planets discovered as a function of year. 1995 was the first planet discovered by the Swiss colleagues. And at the same time, the people in California were looking for this. But they thought a planet goes around the sun like Jupiter in 20 years. So they were going and surfing, not looking at the data. And the Swiss people, they're always to the work. Yeah, 100% concentrated. And so they discovered it, because this planet they discovered goes around in a few days. It's amazing. So they could, then the people in California looked at the data, they found it too. Too late. Sometimes if you're at Fiji, I understand why there's no Max Planck Institute at Fiji, because just simply you have other things to do. I understand it's a beautiful place, but sometimes it's good to live in a place like this where it's raining all the time and it's cold, because you get something done. And then with time we saw more and more of these planets wobbling. Yeah, that is what. But then we ran out of signature, because we had to go farther and farther away, and by 2013 the number of planets you see through the wobbling disappeared, because we had seen the close but not the distant ones. And then came Kepler, and Kepler was now looking at these transit things and looking for dips in the light. And you know how much it discovered in 2014? 800 planets in 1 year. It just tells you, if you have a new instrument, you open new windows to the universe. That's why we're always looking for new windows and new instruments, and we build new instruments, because you discover something completely different. Then Kepler died, but we still had data, and we took care of data and actually analyzed it, and here's another peak. We're from Kepler 2016. And so we know that we have an enormous amount of planets. Actually, we have 8 planets in the solar system. We know more than 3,800 exosolar planets in the vicinity of our sun. We have more than 600 multiple planetary systems. And the embarrassing part for the theorists, and I have to admit I'm a theorist, we have no working model to explain it. We have been working for 50 years on the solar system. We thought this is typical. We worked it out in all details, and now everything is completely different. We have been much too biased with how planets can form. So this is something we still have to do. And here you see the planetary system, just a few, a handful. You see in the middle is the star, and around the star, the planets are moving. And the big dots are big planets, and the small dots are small planets. And you see it's kind of all over the place. There are planets around each star. Sometimes people say there are more planets than dent cones on Earth. That is wrong. But it's getting close. And I wonder why all of this effort if only on one planetary system life could ever form. So I believe just from this reason, and that the ingredients, everything is there, life is probably all over the universe. But we haven't yet found it. It's something we're looking for. Now, I haven't yet shown you a planet. I showed you indications, the dip of light, but not the real planet. But now I want to show you a real planet, an exosolar planet, an image of an exosolar planet. And so now, and I try to stand here, but then I mess this up. Okay. This is a debris disk. This is a solar system where all the gas has been blown away, and you just see the rocks still going around the center. And of course, there might be hidden a planet in this kind of rocky environment. But how do you find it? Well, the first thing is you blur it. It's a 30 million old disk, and you take away all the radiation from the sun, which leads to blurring. And if you do it very carefully, then you see there are a couple of dots left behind. Now, of course, you need to be careful, because you want to find a planet, and then if you see a dot, you immediately think it's a planet. Completely garbage. You need to prove it's a planet. Just because you want to have it, still might not be there. So how do we show that these dots which are left behind are indeed planets? And this is really one of the most amazing observations seen. Here you see the sun, it's kind of blocked, and these white dots are planet candidates. And now we looked at this as a function of time. So every month we made an image, and you see what happens. These dots are moving. They follow precisely Kepler's laws. They do precisely what planets do. They orbit around the sun with precisely the dynamics we know. So we are pretty sure that these are the first planets ever discovered. So there's no question there are planets out there. So let me stop by just saying again, look, we live at a very, very, very special time, as I told you. And while you sit here and enjoy the dinner later on, out there is this ear of mankind, the ALMA Observatory in Chile, which looks at the sky, listens to the sky, and finds the planets and whether there's life out in the universe. Isn't that fascinating? Thank you very much. So I don't know what is next. I can continue. I have a talk about black holes with me in case. No questions. Okay. So do you have some questions or remarks? Yeah, please.
So the solar system is expanding. The universe is expanding, right?
Mm-hmm.
There are many theories for the expansion. And we can build solar sails to travel the universe.
Mm-hmm.
Which role do you think plays light in the expansion?
Well, as far as we know, you don't need light for space to form. It's just a part of space itself. Actually, it's part of gravity. Gravity, which is written down in Einstein's general relativity, has a source term for space. It's most amazing. Gravity, on the one hand, allows things to accumulate and condense, but it has also a source term for space at the same time. So, and you don't need any light and nothing by this. Space itself accumulates. You have a little bit of space and it doubles and it doubles and it doubles and it doubles. It's just being created from nowhere. And you can now fill the universe with light, but it would also, you could have an empty universe, just expanding. That's possible too. So if space is something different to light. But space and time is actually the combined thing. It's a very fascinating story because you don't know what is space and what is time. You can, it's actually, I don't even know what time is anyway because it's very hard. How do you know what time is? And actually the interesting thing is, time is different depending on how fast you, for example, move, as you know. And actually where you sit. So my feet age a little faster than my brain because they are closer to the center of the earth. So I actually wanted to build a little app where you basically see how much your time runs. When you walk, time runs a little shorter. It's good for your health, yeah, anyway. And when you're a little on the hill, your time runs a little faster, okay? So I think it would be fun just to have this and say, oh, today I saved a nanosecond because I walked so much. And I don't know, this app doesn't exist. We should do it. Yeah. Okay. Some more questions? So here. Oh, it's okay, I can explain.
There was recently a picture of a black hole in the media, and there was a lot of excitement about it. So maybe you could explain to the audience why there was so much excitement about it.
Well, it is...
How can we see a black hole?
Yes,
you know what I mean?
You see it because you don't see it. It's as simple as it is. You know, you see something in between this ring, and usually when you look at the space, at space, you always find something, a star or something. But this is absolutely dark. So you know there is something which blocks the light, but it's not gas. It's empty. It's empty space, but no light goes through. And we see this ring of fire, so to say. We see exactly at the distance where Einstein's theory predicts it, we see light being captured in a ring, this donut. And that light, it's very hard to bend light, actually. The Earth does a little, the sun does a little bit, but there must be something very massive to bend light and capture it. Just the right distance. So up to now, we only thought black holes exist because they attract the surrounding stars. It looks like this, but this is a clear evidence. There's no question anymore these black holes exist. And it's good to know, because you better know when you get close to a black hole, you'll be better take a side trip, because it's fascinating. I'm sometimes wondering whether I should fall into, because it's fun. If the black holes are big enough, you don't even realize it. The only problem is you can't get back, because when you want to go back, you have to go back in time, because time and space turns around. So you move in through space, but the way to go back is through time, backwards in time, which is a little difficult. We haven't yet figured it out. But, just understanding that this exists and seeing it is like the planet. Many people don't believe until they see something. Same with me. You can speculate about everything, but once you see it, and there is this shadow, it's a ball in space with nothing. And actually, when you fall into the ball, it's in a whole new universe. It's bigger than our universe, but a different story. But yeah, so it's fun. I could talk about this for another hour, as I said. Oh yeah, so now they wake up. I don't know. Let's start over there, please. Yeah, bitte. Yeah. Picture.
What happened with yourself? Because there was a time before Alma,
Yes.
and everything was clear, and you had your theories, and you saw it, and Alma came, and suddenly it was different.
Sure.
Did you go into depression?
No, just the opposite. Well, how boring would it be if all what I have thought about would be true and I could go home and do something different? The universe is so fascinating. You just don't pretend you know it all. You do as good as you can, and you wait for the next surprise. And I love it. I know in the 1,000 years everything will be different, but we participate in this. You experience it. And that is all you need. You don't have to be at, the way, wie sagt man denn, der Weg ist das Ziel. Doing it is the fun. Not when it's accomplished and you have to think of something new. No, I love it, this evolvement. And actually it's something really funny. Why can we do this? And it's something I think where we are really, really important. When I give these talks to kids and so on, they sometimes begin to wonder now, I will die and whatever, son will die. Isn't that boring, bad? And so why I'm here then, yeah? And I tell them, look, you're here because you are the first object in the universe who knows the universe is beautiful. Because the universe doesn't do it by itself. Yeah? We sit here, we try to give it a history, we try to understand it. And this is a new quality for the universe, which we only we can give. So working it out is something which, and that's why I think I'm so excited about this, because it's our nature. It goes beyond survival. Clearly, I didn't have to do this for survival anymore. We are beyond survival, fortunately, and we can now enjoy it. So this is maybe one of our roads. Yeah. Between da hinten und dann. Yeah. At the moment, it looks like it will expand forever, which is good, because if it expands forever, it can always form new structure. The entropy is basically a state of maximum randomness. Yeah. No, they are not big enough. There will be always new structure formed. As long as the universe expands, entropy is kept low. And you can build new structure. So our universe will live on as long as it expands, and I hope it expands forever, just because of this reason. Yeah.
You said you're a theoretical person. Yeah? Now you tell us about ALMA generating huge amounts of data. How do you actually work? You download them, you wait?
Yes, this is here sits the CEO of the LSZ, and we need more computing time from you. Basically, and we need storage. Yeah, the problem is right now we get to a phase where we have petabytes per night, which we can't store anymore. So we need intelligent computers and software that selects out of the data the most exciting data. This is a big problem if you want to discover something, because it's obviously not what you know. You need to look for data that you don't know. But how do you then select it? It's a wonderful, tough question. And of course, machine learning and artificial intelligence must be part of that. But the other thing is, of course, I don't want artificial intelligence to work it out for me. I'm here and I want to work it out before this computer tells me what happened. Yeah? So there's a challenge right now for us. But it's big data and data handling, which is most important. Also, the data shouldn't be wasted. We need to store it for the next generation. you can't put it into your desk anymore because it's not anymore on the paper. It's somewhere digital. And data, you might say you can do it again. Not, because everything is evolving. Also stars evolving. When you want to understand how stars evolve and so on, you sometimes better get the time sequence. So it's something very fascinating, and we are working on this, you know, very well. Yeah. Yep.
The early state of the universe was expanding, right? It was expanding quite fast.
Yeah, sure.
How was it possible to form galaxies?
Sure. That's a good question. If it would expand too fast, all the little density fluctuations which were there would be smeared out. So it was just expanding fast enough so that not all the material was collapsing into one point, and the universe was collapsing, but not so fast that everything was smeared out. It was just the right speed, so if you had a little fluctuation locally, it could basically decelerate the expansion. Gravity can also decelerate the expansion of the universe if it is an overdensity, enough for structure locally to form. It's really fine-tuned. It's not a big mess, everything collapsing into one point. It's not something everything exploding, just has the right expansion velocity, which is fun. It could be anything else. And we wonder why this is so. Is it because we are in the entropic principle? Because otherwise you wouldn't exist. But it's only an excuse, you know. I better want to work it out from first principles. Maybe there's some first principles where there are 10 to the 500 universes and we live on one of them where things were right. It's a fascinating question. We don't know the answer. Yeah, Pichon.
Question, you said that we have actually just one thing in close distance to fear, which are astronauts. And I asked myself, what, because you mentioned it, we need to find a solution for that. What did you mean by that?
Asteroids. Yeah, well, you see, we get now information about the orbits of the asteroids. And people can figure out with some precision that the next 20, 30 years an asteroid will not hit us. But the solar system is chaotic, and you can show that there's no way you know in 100 years what an asteroid does. It's impossible. And we have kilometer-sized asteroids going by the Earth almost every week. And you hear it again, oh, an asteroid just flew by, we didn't see it. So there is a real danger, and it will happen. What can we do? Well, we can deflect asteroids. There are mechanisms to deflect them. The only problem is it has never been tried. And it's like driving on the Autobahn. If you haven't tried it, you might mess it up. So I think it would be really be for a company or so, it would be so rewarding if you say, okay, I invest the money, we fly to an asteroid, we show it works, we have the technique, so if something comes in for the next generations, there's a shield for the Earth. It would be so rewarding. You know, if you mess up your company for other reasons, you can bring it up again through this mechanisms. And it doesn't cost so much compared to what the messing up costs. So, I mean, but it's another talk again. So there are mechanisms. And it is not done. Why is it not done by space agencies? Because space agencies have limited amount of money, and they need to do science. And there are all these scientists who say, okay, we already have so little money. So some NASA, and so they always want to do it. Russia wanted, you know, Chelyabinsk, there was a thing coming down. Nothing, it's already... You know, you remember what it was 20 years ago, whatever, which had this big explosion. Then Putin said, oh, we do something. And then he ran out of money. Nothing has happened. And so a space agency will never do it because it's you need private sector to do it. But, you know, in Germany, private sector is not accessible easily for a scientist. That's the story we have. And we don't want the US to do it. We want to do it ourselves, of course. Don't rely on the US to save us. You see it right now. Yeah. So, okay. I think that's it. Thank you.